Right, so we're going to get started. Continuing on with carbohydrates, and then we'll get into amino acids. Okay, so we left off carbohydrates, just going over some of the monosaccharides that you need to be familiar with. Again, this is kind of like, you need to know that like the definitions of these. So it's going to serve you to know that glucose is the same thing as dextrose and blood sugar. We have, outside of glucose, we have fructose. Fructose is obtained from sucrose, and we'll talk about sucrose in a second. Sucrose is a disaccharide. It's a ketohexose with a form of C6H12O6. So same molecular formula as glucose, but whereas glucose is an aldehexose, or the carbonyl group is at the end, fructose has a ketohexose. Its carbonyl group is one carbon in. The sweetness, this is twice as sweet as sucrose. So honey will have glucose and fructose. Remember, glucose is an aldehexose, meaning your carbonyl group is at the end. Fructose is a ketohexose. There's our carbonyl group. Okay, so galactose is an aldehexose. D-galactose. So we've got our aldehyde at the end, 6 carbons, not found free in nature. We get it from a disaccharide called lactose. Has a very similar structure to glucose, except the OH on the 4th carbon, 1, 2, 3, 4, right here. The OH on carbon 4 is on the left here. The OH on carbon 4, 1, 2, 3, 1, 2, 3, 4 is on the right. So just a small difference. All 3 of these are hexose, 6 carbon chains. In the body, glucose is blood sugar, and a normal level of that is 70 to 90 milligrams per deciliter. You can do a glucose tolerance test, which measures your blood glucose for several hours after ingesting glucose. So you'll usually fast, and then you'll take this glucose drink that is disgusting. If you've been pregnant, you might have had to take one of these tests, these blood sugar tests, and you have to drink this stuff, and it's really gross. And what it does is it'll spike your glucose and then bring it back down. And if you're hyperglycemic, you'll have a much higher blood glucose level. If you're normal, you're in this mid-range. And if you're hypoglycemic, you'll be lower, or you don't have quite as high blood glucose. Okay, so we're not going to get too much into this. So this thing for right here, it says draw the Fisher projections for D-fructose and L-fructose. I don't need you to be able to draw them, all right? But I would expect you to be able to identify whether they are D or L. So I don't expect you to have, this fully memorized, but you do need to know that this is D and this is L. How do we know it's D? We go to the chiral carbon farthest from the carbonyl group and we see where the OH is. Here the OH is on the right, right goes with D. If it's on the left, L, LL. All right, so with these usually 5 to 6 carbon chains in our carbohydrates, they're actually more stable if they curl in on themselves and form these sugar rings. Okay, so this ring is known as a Hawthorne structure, and they will show the carbonyl group will usually sit over here or over here somewhere, and then it wraps around itself. All right, so each of these points here, we've got a carbon here, and specifically we have a chiral carbon. So carbon here, chiral carbon here, 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 and here. And we've got the OHs coming off. Do I expect you to be able to draw this? No way. But you do need to be able to identify whether it's a pentose or a hexose. And then we have to be able to identify an additional structure which classifies it as an alpha or a beta. So this is going to give you directions on how to draw. No worries, Whitney. This is going to give you directions on how to draw a Hawthorne structure. I don't expect you to draw a Hawthorne structure, okay? But I do expect you to look at a Hawthorne structure and give me some information based off of it. So this would say, if you were going to draw it, we'll go through it just so that you can see where this cyclical sugar structure is coming from. So you take the Fisher projector and you turn it on its side, and then you curl it up on itself. So then it wraps in up on itself. And what's happening is the OH here ends up bonding to the O here. So we get this cyclical structure. So when you see something like this, it can also be drawn like this. Again, I don't expect you to draw these. You do need to be able to identify if they're alpha or beta though, okay? So when determining if it's alpha or beta, you need to go to where the OH group on carbon 1 belongs on the ring. So this is carbon 1 right here. This is 1, 2, 3, 4, 5, and then that's the 6th carbon. Looking right here, if the OH points down, it's an alpha isomer. And I know that's kind of weird because like usually you think of alpha as sitting like above, but in this case, alpha points down. The beta isomer is the one where the OH on carbon 1 points up. So this one over here would be alpha D-glucose. Again, from this structure, you can't really identify that it's D-glucose. I would have to tell you that it's D-glucose from the ring structure. If I had it in the Fisher or stretched out, you could tell me it was D. This over here would be beta D-glucose. So both these are D-glucoses. This is an alpha and this is a beta. So mutual rotation of alpha and B D-glucose when placed in a solution. So when I put this ring sugar or carbohydrate into solution, a lot of times it will open up and you can get rotation of this. So you can actually have alpha and betas kind of rotating. In a solution, usually it'll be 36% alpha and 64% beta. It prefers being in this beta alignment than in the alpha. And then at any given time, there is a small amount that is sitting in this open chain. So here are, this is the Hawthorne structure to fructose, which is a ketohexose. The difference here, these were, this was for glucose. Remember, glucose is an aldohexose, okay? If you notice, the shape is slightly different. It kind of looks like a little house. So that's one way to remember whether you're looking at an aldohexose or a ketohexose. The ketohexose, key to the house. Think of this as the the point on the house, and this is the roof. When determining if it's alpha or beta, instead of being on the first carbon, you're going to look at the second carbon, because look at here, the first carbon, this is carbon 1, 2, 3, 4, 5, and 6. This first carbon, when it's a ketohexose, is not a chiral carbon. So we want to go to the first actual chiral carbon, which is the second carbon in the chain. So again, if the OH points down, we say it's an alpha. If the OH points up, we say it's a beta. So this thing here says, write the cyclical form of D-galactose. No, I don't expect you to write the cyclical form, but let's look at the cyclical form. You would have to be able to tell me that this is a alpha hexose. And you'd have to be able to tell me that it's either alpha for this one or beta for this one. So let's go to that worksheet and we can do some of these together just to understand a little better what I'm looking for. Okay, so we did the first section where you were able to decide whether they were aldo or keto, triose, tetrose, pentose off of the Fisher projections. Now we're going to look at these structures here, and this is state whether each of the structures is alpha or beta, and whether it's a ketohexose or an aldohexose. So real easy. If it looks like a little house, it's a ketohexose, the key to the house. All right, so this is a ketohexose. Whether it's alpha or beta, let me write ketohexose. If you're kind of thinking, well, this is like really simple, it gets more complicated. You guys aren't going to learn about the more complicated components of this though. For right now, I just want you to be able to identify them. So this is a ketohexose. There are 6 carbons, and if you want, let's count them out. 1 carbon here, 2, 3, 4, 5, 6. Just like in the Fisher projections, remember they didn't write the chiral carbons? They don't write the chiral carbons. You assume those are the points. Okay, so it's a hexose. It looks like a house, keto, and then we have to determine whether it's alpha or beta. Well, where is the OH group on that second carbon? It is pointing down, so this is an alpha ketohexose. This next one here, this isn't the house. This is more like a boat shape. The boat is an aldohexose. We want to decide whether it's alpha or beta. Okay, go to that first carbon. There it is. Or the first chiral carbon. And then look at what the OH is doing. In this case, the OH is pointing up. Pointing up makes it a beta. Okay, I want you to do 8 and 9. You may not want to, like, if you don't have this printed out or you don't have this like up on your computer, you can write this structure out. You may just want to write number 8 for the lab and then put the answer. These can be kind of a pain to write out. And again, I wouldn't expect you to look at this, and I wouldn't expect you to know that this is fructose or glucose. But I would expect you to know that this is a 6 carbon chain. So this is a hexose. It makes a house shape. So it's a ketohexose, key to the house. And my OH is pointing down. So this is an alpha ketohexose. And looking at this guy here, I wouldn't expect you to know that this is glucose or a beta or a D-glucose, but I would expect you to know that it is a 6 carbon chain. So it's a hexose. It's an aldo shape. Aldohexose. It looks like a boat. I don't know how you want to remember that. Al sitting in the boat. Okay. I just remember this one's the house. So what's happening with our OH group on that first carbon, first chiral carbon? It is pointing down. So this is an alpha aldohexose. This last one here is a disaccharide. So the questions in here said classified as one of these or a disaccharide. This is two sugar rings that are linked together. So I'm going to call it a disaccharide. I don't expect you to classify your disaccharides as alpha or beta. I just want you to write it out as a disaccharide for now. Okay, any questions on that? Hopefully those first two, hopefully this feels a little less intimidating than if you had like read the chapter and be like, oh my gosh, what is all this stuff? You don't need to know a crazy amount about these Fisher and Hawthorne structures, but we are going to need to know some, a good amount of definitions here. Okay, so let's open this back up. They talk a little bit about chemical processes in monosaccharides. So like if you've ever heard of sugar alcohols, which are like D-sorbitol, D-Xol. This is all the like fake sugars that they put in things like sugar-free gum and stuff like that. They're called sugar alcohols because what they've done is they've taken a regular sugar or a simple sugar, like here we've got glucose, and they oxidize it so that it becomes like an alcohol. And when they oxidize it, they like, so here we've got our glucose, and they go ahead and, or actually in this sense for the sugar alcohols, they reduce it. So these are known as reducing sugars. So if you can reduce this reduces down. And now we have an OH group at the end, which makes it an alcohol. These are the fake sugars. So there's a similar structure, and it produces like sort of a sugary taste, right? It's kind of off tasting, but there's like a sweetness to it, but your body doesn't break it down in the same way it would break down glucose. So that's why it's calorie free or whatever. Sugar alcohol here's sorbitol. They put this in diet drinks and sugarless gum. This says write the reduction of mannose, D-mannose. No, we're not going to do that. All right, so don't worry about that. But you can see that what has happened to D-mannose, D because the OH group is on the right. When you reduce it, remember reducing is putting more hydrogen in. So they change this OH, or rather this O double bonded to an OH. So they put a hydrogen right on there, and that changes this from an aldehyde to an alcohol. Mannitol is its new name. All right, we're not going to spend a whole lot of time about glucose. Let's talk about disaccharides. Okay. So our simplest structure was a monosaccharide for carbohydrates. Now we've got disaccharides. There's going to be 3 disaccharides that you need to know information on. Here's some images of, here's lactose. Lactose is a disaccharide that's found in milk and milk products. It contains galactose and glucose. Lactose and glucose. Some people can't digest these, can't break them down. So here are the saccharides that you need to know. 2 monosaccharides together make a disaccharide. Is formed when 2 monosaccharides combine in what's known as a dehydration reaction. So remember, dehydration is when you give up a water. So glucose will combine with another glucose, and that produces maltose. Okay, so maltose equals glucose plus glucose. And actually it pops out of water as well, hence the dehydration. If we have glucose and galactose, that becomes lactose. That's our like milk stuff and dairy stuff. And then glucose plus fructose is what makes sucrose. So sugar, like table sugar is sucrose. Are there more disaccharides than this? Oh yeah, but these are the 3 that I expect you to know. So let's look at some information on maltose. Maltose is a disaccharide. Sometimes it's called malt sugar. It's combined or composed of two D-glucose molecules. So glucose, maltose. It's obtained from the hydrolysis of starch. So if you take starch and hydrolyze it, you can get maltose. It's used in cereals, candies, and then brewing. We can find it in both an alpha and a beta form. So let's look at the two different forms. Okay, so this is the structure of a glucose and a glucose. Now, these two things have to stick together, all right? How do they stick together? Well, if I put my two rings next to each other, what happens is that the OH from this glucose and an H from this OH will come together. And what is that? That's H2O, right? So that's where the dehydration is coming from. And then these two things will stick together and this oxygen will sit right in between them. So this is evolving into this right here. This bond, which you do need to know the bond, this is known as a 1,4 glycosidic bond. So maltose has a 1,4, specifically an alpha 1,4 glycosidic bond. Now, glycosidic bond will always be in there. Where does the 1 and the 4 come from? The 1 is because it's on carbon 1 for this glucose. The 4 is because it's on carbon 4 in this glucose. See, 1, 2, 1, 2, 3, 4. So 1, 4 glycosidic bond. Where is the alpha coming from? The alpha is coming from this carbon 1 was pointing, the OH was pointing down. So down gives us the alpha. So you will need to know that maltose has an alpha 1,4 glycosidic bond. Now, if I was to look at this whole thing as a unit, this whole thing as a unit, this is known as alpha maltose. Why is this alpha? Well, how do you do that? Go to your sugar ring on the right side and see what its OH is doing. Don't worry about this one. Look at what this one's doing. If it's pointing down, it's an alpha maltose molecule. So this is a disaccharide that has an alpha isomer and it has an alpha 1,4 glycosidic bond. Okay, so there's two alphas going on here. Hopefully the next page. Oh, come on. It won't show me the beta one. Okay, so if this was the beta isomer, it would still have a 1,4 alpha glycosidic bond, but the beta isomer would have the OH sitting up here. All right, so if this happened to be up here, we would call that the beta maltose. We will go over a worksheet that looks at some of these, okay, in more detail. So lactose, instead of it having glucose, it has glucose combined with galactose. Now this one has a different bond because galactose, its OH will point up. It's beta galactose. So the OH from here will combine with the H from here. Those stick together to form our water. So that's why it puts out a water. But the OH points up, making it a beta. So this type of bond is a beta 1,4 glycosidic bond. So with lactose, instead of the alpha, we get the beta. See how it goes? It makes like a kink like this. Whereas the last page, it pointed down for both sides. Here, this is pointing up and this is pointing down. And that's important. Those bonds are important because our bodies can digest certain bonds and break the sugars down, and sometimes we can't break other ones. Like people who are lactose intolerant usually can't break this beta 1,4 glycosidic bond. It's still 1,4 though, because it's on carbon 1 here and it's on 4 here. This whole lactose is a alpha. It's an alpha. Right? If this OH happened to be on top, we would say it's a beta lactose. So do you know the bonds? We've got another one, sucrose, which is table sugar. Oh, another thing I want to note too, maltose and lactose, write down somewhere that those are reducing sugars. What that means is, you see how this ring here is uninhibited by a bond? This ring is locked up, right? It's bonded in this glycosidic bond. So I can't open this ring up, but this ring is free to open up. When the ring is free to open up, it's easier for it to be reduced, all right? Same thing here. This galactose is locked in a chain, so it cannot be reduced. I can't do anything chemically really with that. But this one over here is open, so this one allows it to be a reducing sugar. Versus here is an example of table sugar. Do you see how the bond here is locking this ring up? It's stacked on top of this one, which is also locking this ring up. So table sugar is not a reducing sugar. Just know that. Can't reduce. Now this guy's a little different, table sugar, in that the rings are stacked on top of each other. We have an aldehexose, glucose, and then we have a ketohexose, which is fructose. In this one, the glucose, the OH from carbon 1 will bond with just the H on the OH from carbon 2. So we call this, and this is pointing down and this one's pointing up. So we're getting like an alpha and a beta. So we call this bond an alpha beta 1,2 glycosidic bond. And you will need to know that. So you either memorize it or you get it conceptually, but you do want to know that sucrose has this alpha beta 1,2 glycosidic bond. Or rather sucrose. So there's a better picture of it. So we can see here's our glucose, here's our fructose. They stack on top of each other and then they form their bond right here. The oxygen attaches to this carbon 1 and to this carbon 2, and it puts out a water. We just call this sucrose. We don't call it alpha or beta sucrose. Okay, there's not going to be an alpha or beta isomer for this. Here's some artificial sweeteners, aspartame, blah, 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 blah. All right, let's talk about these. So identify the monosaccharides in each of the following. So in lactose, what are the things that we have in there? So we have galactose and we have glucose. One thing to remember, every single one of your 3 will have a glucose, at least one glucose. All right, it's the other thing that changes. So lactose has a glucose, maltose has a glucose, sucrose has a glucose. They all have a glucose. So lactose has a glucose and a galactose. Maltose has a glucose and a glucose, 2 glucoses. Sucrose has a glucose and a fructose. So you will just want to know these. Let's look at that worksheet again. I think it's helpful. All right, we're going to skip past this stuff. We're going to go down here. So for each of these, it says, it tells you what it is. All right, so don't get freaked out and think, oh my gosh, I got to know that this is maltose. I would tell you it's maltose. But for the following disaccharides, state the monosaccharide units. So in this one, we want to say, what are the 2 things that it makes that make it up? We want to B, tell the type of glycosidic bond. C, we want to determine if it's alpha or beta or if it doesn't have an isomer. And then we want to also decide if it's a reducing sugar. So let's look at this one here. So this is maltose. So what is maltose made of? Well, maltose is made of it always has a glucose. So we're never going to be wrong writing glucose. And if it's maltose, it also has a glucose. Okay, 2 glucose. Specifically a D glucose. All right, B, it says, what is the type of glycosidic bond? So you can memorize it as a 1,4 alpha glycosidic bond, or you can look here and say, oh, this is carbon 1. This is 1, 2, 3, 4. This is carbon 4. So it's a 1, 4. And this is pointing down, which makes it alpha. So an alpha 1, comma 4 glycosidic bond. Now we want to determine if this is an alpha or a beta for the whole molecule. All right, so this one here is talking about the molecule as a whole. Well, I go all the way over to the right and I see what its OH is doing. And in this case, the OH is pointing up. Up is beta. So this is beta maltose. And then we want to ask ourselves, is this a reducing sugar? Do I have the opportunity or the potential to reduce it? I do, because this is open here. So this ring could unfold and it has the potential to reduce. So we would say that this is a reducing sugar. I want you to do this one here, number 2. This is lactose. So I want you to tell me, what are the monosaccharide units? What type of bond does it have? And what isomer, anomer is it? And then if it's a reducing sugar. Okay, so this has glucose. And if it's lactose, it's also got galactose. The type of bond, so we're looking at this here. This is carbon 1, this is carbon 4. And this is pointing up on the first carbon, so that's a beta. So it's a beta 1, comma 4 glycosidic bond. If you're like, I don't know how to read that off of there, well, then you have 3 bonds to memorize. So just know them. Is this an alpha or a beta lactose? Let's go all the way over to the right and see what is its OH doing. Here the OH is pointing down, so this is an alpha. And then is this open here to reduce? Yes, this ring is free to open up in solution, so we would say that this is a reducing sugar. So some of this is sort of memorizing, some of it's being able to identify. I'm going to do one more with you. I'll leave this one for you to do on your own, the maltose, the second maltose. These are very, very similar to each other. They're just a difference of where its OH is pointing. This guy here is sucrose. Okay, so sucrose is, every one of them has glucose that you need to know, and it also has fructose. Looking at its bond, it's this funky thing here. A little bit different than our other guys. These are stacked. This is on the carbon 1, this is on carbon 2. So, and this one's pointing down and this one's pointing up. So this is that alpha, comma, beta, dash 1, comma 2, glycosidic. Sucrose doesn't have an alpha or a beta. And this is not a reducing sugar, not a reducing sugar. Why? Because both of these this is locked up right here. You kind of think of that glycosidic bond as like a lock and key. It's locked there. This ring is locked here. Neither one can open on the right side to do any sort of reducing. You may be thinking, well, why can't it open up on this other side? It's the way that it's drawn. It always puts the more oxidizing or reducing end on the right-hand side. So this is the side that could possibly open up, and we just can't here. Any questions on that? Really just kind of memorizing. Okay, let's head back over to the slides. I would like to get into amino acids just a little bit today as well. You can look through blood types if you're interested in blood types. It has to do with some different monosaccharides. Okay, last thing that I want to talk about, which is heavily definition based, are polysaccharides. So over here on the right, we have the polysaccharide cellulose. We can find it in, here's cotton. We also see it in plants. This is, yeah, in lots of plants. Thing about cellulose is it's these little glucose rings, and every glucose ring is connected by this beta-1,4 glycosidic bond. And this specific beta-1,4 glycosidic bond is something that we can't digest, hence why we can't digest cellulose. We can't eat a tree for fuel because our body can't get to the sugar rings. Cows can, other animals can, we can't. So what is a polysaccharide? Polysaccharides are formed when monosaccharides are joined together. We have amylose, amylopectin, and cellulose. All of these, amylose, amylopectin, and cellulose, are polymers of alpha D glucose. So they're just a bunch of these alpha D glucose rings. So here's the, excuse me, here's the simple monosaccharide. We just start chaining those together, poly meaning many. So we chain a bunch of them together and we get a polysaccharide. So amylose and amylopectin, the structures of amylose is a straight chain polysaccharide of glucose units. So this right here would be our unbranched amylose. Amylopectin is slightly different in that it gets, it has a branch chain. So this is just one single chain, and it usually kind of coils up around itself. Think of this as like a pearl necklace. Amylopectin is like a little bit more of a bedazzled pearl necklace. So you've got your pearl necklace, and then you've got these chains of additional pearls hanging off. Usually for the branch chain, you will get what's known as an alpha 1,6 glycosidic bond. So coming off of the main chain at carbon 6, it'll attach to a carbon 1, and you get this sort of chain hanging off the end. Both of these come out of starch. So that's why they've got this potato here. Makes up amylose, which is the single chain, makes up about 20% of your starch. How long are these chains? Anywhere between 250 to 400 or 4,000 of these alpha D glucose molecules connected together. All of them are connected with a 1,4 glycosidic bond. Okay, so each one of these connected with that alpha 1,4 glycosidic bond. It's called a straight chain polymer, even though the polymer of amylose usually will coil in around itself. The reason they call it a straight chain is just because it doesn't have any branches. It's just a single chain that sort of curls up on itself. Now, amylopectin makes up as much as 80% of starch. So this is the remaining part of the starch, the majority of the starch. It's a branch chain polysaccharide. So it has little accessories coming off of the main chain. This will contain two different types of bonds. It has the main chain alpha 1,4 glycosidic bond. So it's similar to amylose in that it has the 1,4, but then it has this 1,6 glycosidic branch or extension. In general, starches will hydrolyze really easy into water and also in acid to give us smaller saccharides called dextrins, which we can then break down into maltose and then break down into glucose. So our body will take the starch and break it down into a smaller chain, and then it'll break it into a disaccharide, and then it'll break it into the glucose that our body then can eat. This process requires energy, right? So when you can eat complex carbohydrates, like things from potatoes, getting your sugar from potatoes, your body has to work to break it down versus just getting the glucose from like, let's say some high fructose corn syrup, right? It doesn't really have to do much to get to the glucose. We have another polysaccharide that you need to know, which is glycogen. Glycogen is a polymer or a polysaccharide of glucose, so it's all glucose, that is stored in the liver and muscle of animals. So it's kind of like a reserve. This will hydrolyze in our cells at a specific rate that maintains blood level of glucose and provides energy in between meals. So if we didn't have this glycogen stored in our liver and our muscles, we would eat, we would get the glucose, and then we would crash, right? But we keep like a relatively maintained blood sugar level because our body will break down this glycogen. Glucose, the glucose units in glycogen are joined similarly as 1,4 glycosidic bonds with branches that are alpha 1,6 glycosidic bonds. So this is a branched polymer as well. And those are about every 10 to 15 glucose units. So glycogen and amylopectin, both of these are branched. Amylopectin is in starch though, glycogen is in our bodies. All right, then we got cellulose. So cellulose is the major structure in wood. It is a polysaccharide of glucose. So all of these polysaccharides are just glucose. We're not worrying about fructose and we're not worrying about galactose with these. This is a little different though, and that it's an unbranched chain, so it's a single chain, but the bond is a beta 1,4 glycosidic bond. So it can't form any sort of hydrogen bonds in water, so it's insoluble in water. So we don't see wood, like the sugars uncurling in water if they come from cellulose. It gives the wood a rigid structure to the cell walls. It's more resistant to hydrolysis than starches, so it doesn't tend to want to hydrolyze. And the important thing here for us is it can't be digested by humans because we don't know how to our bodies don't know how to break down this bond. So that beta 1,4 glycosidic bond is what prevents us from receiving nutrients from cellulose. So you can eat bark all day and it's not gonna do anything for you. So here is a picture of cellulose. You can see it's got that pointing up and pointing down bond versus all these guys over here, which had, where they both point down, that alpha 1,4. So looking at this here, it says identify the polysaccharides and the type of bonds in each. So this over here is a tree. It would have cellulose. So we would have that tricky beta 1,4 glycosidic bond that we can't digest. This over here has amylose and it also, amylopectin in this. It's got the single chain 1,4 glycosidic bond, and it also has the 1,6 glycosidic bond as well if it's the amylopectin. So it's kind of a bunch of definitions. You will get practice with this in the lab. I'm not going to go over all the definitions on the lab because I feel like that's something you can handle. It's not a whole lot of critical thinking, but let's take a quick peek at it. So what you'll see is the remainder of your lab is these two sections right here. So this one says describe the similarities and differences. So amylose and amylopectin, you got to tell me what's similar about them, what's different. They're both found in starches. They're both made of glucose. They both have certain bonds, but this one is single chained and this is branch chained, right? So you'll go through all of these and compare them. Here, you've got just a bunch of definitions and then you want to match them up. So like, for instance, this first one, a disaccharide found in milk products. Okay, that would have to be a disaccharide. It would be lactose. All right, so you just go through and match these up. I think y'all can handle that. And then that is the end of carbohydrates. Okay, so Really with carbohydrates, the definitions, know your disaccharides, be able to determine whether these rings are alpha or beta, what type of bonds the rings form in a disaccharide, and then be able to read your Fisher projections. Tell me what a chiral carbon is. It has 4 different buddies. That's really should be most of it. I'm trying to think if there's anything else. Got our chiral carbons. Be able to tell me if it's a ketohexose, aldehexose, D or L isomers. Yeah. Okay. Let's move on to the last chapter because I don't want to have to smush it all in on Thursday. This last chapter is sort of your biochem for the semester. It's on amino acids, proteins, and enzymes. So, all right. So proteins and amino acids. Protein molecules, compared with many of the other compounds we have studied, can be very, very large. All right. These are huge, huge molecules. The horns of this animal are made out of proteins. Also his fur and his eyes, pretty much his whole body is composed of different types of proteins. Now different proteins will have different functions, and we will learn to give names to some of these proteins and some of the amino acids. So as far as proteins in the body are made of polymers, and they're combined with, or can be made up of 20 different types of amino acids. So amino acids are sort of the letters to the words of the protein. And then proteins will come together to form the literature that is your body. Different characteristics and functions depend on the ordering of the amino acids that make up the protein. So depending on what sort of amino acids are combined together, you'll get different types of proteins. They form structural components like cartilage, muscle, hair, and nails. The ordering of these amino acids and the type of the amino acids can give you things like cartilage versus things like hair. We also have proteins used as they function as enzymes to regulate different biological functions like digestion and cellular metabolism. We also have proteins like hemoglobin, which helps to transport oxygen through the blood. So proteins do a bunch of different things. There's structural ones, there's functional ones, there's transportational ones. Here are different classes of proteins. So structural, contractile, transport, storage, hormonal. All of our hormones are different types of proteins, enzymes, and then protection. I don't really expect you to memorize, that collagen is a type of structural protein, but it is. All right, so let's talk about an amino acid. Amino acids are the molecular building blocks of proteins. We can break amino acids down into something simpler. We could break them down into atoms, but all amino acids have sort of a similar structure with an accessory end. So looking at this amino acid right here, this is a simple amino acid. All amino acids will have a central carbon that's known as the alpha carbon. So in this one, this is the alpha carbon right here. The alpha carbon will always be bonded to 2 functional groups. One of the functional groups is the ammonium group. So let me draw. So this is my alpha carbon, and it'll have an ammonia group on one side, and it'll have a carboxylic group on the other side, or this COO group. So this here, this sort of odd shape, this is, and then there's an H, sorry, and then there'll be a little H sticking off of it. This is the same for every single amino acid. It always has these components here. Then it has what's known as an R group. The R group is what differs. This is what defines an amino acid one from another. So in this case, we have a methyl group, right, attached to my kind of amino acid base. Here is the structure. There's my alpha carbon. There's my amino group, the NH3, and then there's my carboxylic group. Amino acids can be classified as either polar or nonpolar. You will have to be able to classify them as polar or nonpolar. You will not have to memorize these. So I don't expect you to know that this is valine, okay? But I would want you to know that this is a nonpolar molecule. How do you determine if it's nonpolar? You go to its accessory group. If it contains just a hydrocarbon chain, so just carbons and hydrogens, we would say that that's nonpolar. If it contains something that's symmetrical polar, or it has any sort of ionic side to it, or an imbalance, we would call that polar. So do you see how there is our alpha carbon, there's our amino group, or our ammonium group, there's our carboxylic group, and then there's the hydrogen. It's the same in both of them, right? This is what changes. This is what gives it its property. So here are some nonpolar amino acids. Look, they all have this same base. What changes is the accessory. So here we just have an H. This is the simplest, glycine. Alanine is a little bit more complicated. It's got some carbons, but all of these we say are polar, or I'm sorry, nonpolar. These guys as well, we're going to say are nonpolar. This guy can look a little tricky because it's got this benzene ring off of it, but we are going to say that this is nonpolar. So an amino acid is nonpolar when the R group is an H, an alkyl, or an aromatic. All right, so that this is an aromatic and this is also an aromatic. That's why we would say that that's nonpolar. Here are some polar amino acids. Polar amino acids have an alcohol, a thiol, or an amide group, amide being NH2. So see how it's got the alcohol popping off of it? This one has an alcohol popping off of it. This has an alcohol, this has an SH. This has the amide and this has the amide. That makes it polar. But again, remember, look at same base right here for every single one. Alpha carbon with the NH3 on one side and the Cu on the other, and then an H sticking off the end. So structural formula of amino acid, an amino acid has an alpha carbon with these three components. The fourth component on the carbon is the R group, which is what differentiates that particular amino acid. And there are 20 of them. If you are going into biochem, you would probably have to have all these memorized. I don't expect you to memorize all 20 of the amino acids. A lot of times with these amino acids, because their names can be a little bit cumbersome, we will just abbreviate them with either a 3-letter or a 1-letter abbreviation. So you can see here for serine, which is an amino with a CH2 and then an OH sticking off of it, we would abbreviate it as SER, comma, or we could SER, or we could abbreviate it as just S. So drawing amino acids, whenever you're drawing amino acids, they will always have this base, right, this thing here, that you do want to be comfortable with. But I don't expect you to know the R groups for everything. All right. There are some amino acids that are acidic. So aspartic acid and glutamic acid, these are both amino acids that have an acidic quality. There are some basic amino acids, which kind of sounds weird, basic amino acid, but they are in fact basic. they tend to have these NH3 groups with them, or the amine group with them. So when looking at this, it says identify it as polar or non-polar. So glycine, this thing, this is the NH3, this is the CO. And then when looking at this carbon has two H's connected to it. It's not actually drawn out for us. I'm going to extend it out. So let's ditch this here and draw it out. So it has an H down here, which is always included in those three components. And then it has an H up here. So the R group is really just this H. That's the simplest amino acid. This is just hydrogen. So we're going to say this is nonpolar. Looking at this one, here's my alpha carbon. Here's one of the limbs. Here's the other limb. There's the H sticking out the bottom. And then we have this thing here. If this OH wasn't there and it was just this, we would say it's nonpolar, but that OH makes it polar. Okay, so you do want to be able to identify polar and nonpolar amino acids. You don't need to know their names. You need to be able to tell me what they are as far as that. Draw the ionized form for each of the following amino acids and write the 3-letter and 1-letter abbreviations. So I don't expect you to draw the structure, but symbol-wise, this would be VAL or V. It's just the first 3 letters. It's not anything complicated. So when expanding out our amino acids, we can have L and D structures. And again, it's associated with where that accessory group is. So if it's on the left, it's L. If it's on the right, it's D. I'm not going to test you on D or L antiisomer or antiimers for amino acids. Yeah, I'm not really going to test you on this, so we don't have to worry about that. Okay. So of the 20 amino acids used to build proteins in our body, there are 11 that we can synthesize in our body. So our bodies can take fuel and different materials that we pick up through eating and make 11 of them. But there are 9 amino acids that we cannot actually create in our bodies, so we have to eat them. We need to receive that protein through our diet. So these are, again, you don't need to have these memorized, but these are the 9 that we require. So if you don't eat protein in your diet, you know, your hair starts to get brittle, your nails start to get brittle, your skin looks kind of dull, because these 9 amino acids, really the only way they're going to get into your body is if you have a certain amount of protein. Doesn't mean you have to get that protein through meat. You can get it through beans and other sorts of vegetarian products, but you do need to be receiving protein. So complete proteins, eggs, milk, meat, and fish contain all of the essential amino acids. Incomplete proteins are grains, beans, nuts. They're always going to be deficient in one or more of them. So if you are if you aren't eating meats, right? If you're not getting these complete proteins, like eggs are great for protein because you get everything you need. But let's say you don't eat these things, you have to eat a variety of grains, nuts, and beans to cover all your bases. So if beans are missing one of those, you got to eat some nuts to cover that essential amino acid. When an amino acid with positive and negative charges has an overall neutral charge, we say that it's isoelectronic, or it's hit its pi point. So this N group over here will have 3 hydrogens and it'll have an overall positive charge. This carboxylic group over here has an overall negative charge. So this positive and this negative balance each other out. We say that this is at its isoelectric point, or its overall neutral. Every amino acid has a specific pH where it's isoelectric, where it's got a positive here and a negative here. For glycine, which is our simplest version, our simplest amino acid, its pH of 6. So when it sits at a pH of 6, this will have a positive charge, this will have a negative charge, and it'll be neutral. So the isoelectric point of any amino acid is the pH at which the charge groups on the amino acids are perfectly balanced and the overall amino acid is neutral. You do need to know this. A positive ion, if a solution is more acidic or a lower pH than its pI. So if we are in an acidic solution, my amino acid will become more positive, and I'll show you why. If we're in a basic solution, it will become more negative. So more basic than whatever its pI is, we get a negative ion. So let's look at this here. This is alanine or alanine. We've got our, here is our alpha carbon. Here are the 3 groups. It's got its amino group, or its ammonium group, it's got its carboxylic group, and then it's got that hydrogen, and then here's its accessory. It's a methyl group. So if I take, this tends to have a pH somewhere between 5.1 and 6.3 is where it's at its pI. Now, what happens if I put this in a pH that is lower than 6? So did we move to, yeah, we're still at the same one. Okay, so alanine at 6, this is a positive and this is a negative. Well, if I add acid to it, I put it in a low pH solution or acidic solution, there's going to be a bunch of H's floating around. If there are a bunch of H's floating around, I can stick an H to this O and neutralize it. I wouldn't put an H over here because this is a positive charge. And remember, an H has a positive charge, so I'm not going to shove that on there. But I can take one of these H's from the water and stick it right here. If I stick it here, what happens to the charge on this side? The charge on the carboxylic side becomes neutral. This side over here stays positive. So my overall charge becomes a +1. So my amino acid now has a +1 charge because I'm in an acidic solution. Think about pH, lower pH, more acid, more H+, more positive. What if instead I put it in a basic solution? Okay, if I take this thing and I put it in a solution that's basic, well, this OH wants to neutralize to water, so it's going to steal an H. Is there an H to steal from here? No, but there is an H I can steal from over here. So let's say I'm going to grab this one. I'm going to take this H, I'm going to stick it on the water. If I stick it, or I'm going to stick it on the OH, which will give me water. What am I left with? I'm down an H. So my charge here becomes neutral. What has happened to this charge? Nothing. It's still negative. So the overall charge of the molecule now becomes negative. We've stolen a hydrogen from this. So in basic solutions, we steal a hydrogen. In acidic solutions, we add a hydrogen. And that is true. It doesn't matter what the accessory is, right? It doesn't matter what this thing is. It could be really simple like this or super complicated. We're playing around with the base unit of the amino acid, right? So when looking at this, we've got our amino acid at the PI. At the PI, and there should be, I don't know why there's not. There should be a little plus here, like that. I feel like that is supposed to be there. So plus there, this is a plus here. This is supposed to be right here, plus. At our PI, which is very specific for whatever the amino acid is, that'd be something I'd have to give to you. At our PI, we have a positive end and a negative end, and those two neutralize each other. If I'm adding H+, I'm going to add a hydrogen to the COO side or the negative side. That makes this whole thing a positive ion. If I go to a higher pH or I'm adding OH, The OH is going to steal a hydrogen, which will make this side neutral and allow the negative side to dominate or become a negative ion. So looking at these two, which structure represents alanine at a pH above its pi, and which one represents alanine at a pH below its pi? So you got to find the alpha carbon. Here's my alpha carbon. Here's my alpha carbon. I'm just going to look at this thing here. I don't really need to worry about the R group or the accessory. That doesn't come into play here. So we're just going to look at this. In this situation, how is this different than what we normally see? There's an H over here that's neutralized this side. So this has an overall positive charge. Positive happens when we have more H plus, right? Where do we get more H plus? In an acidic solution. So an acidic solution would be below its pH, or its pi rather. So this first one is B. The second one over here, what do I see different here? I'm down an H, right? This had 3 H, normally it has 3 H's. Here it only has 2 H's. So I am down an H plus. How do I lose an H plus? I have to be in a basic solution because the base will steal the H plus basic. So I have to be above my normal pi, where 2 would be A. Come on. Any questions on that? It's this, this R end could get super, super complicated, but all you're really looking at when we're talking about pH stuff is this right here in the pi point. Okay, so this thing here, it says consider the amino acid leucine with a pi of 6. At pH of 3, how does leucine change? So if we're at a pH of 3, that means we're acidic, right? 3 is acidic. So I'm going to be adding H plus. Where can I stick H plus here? The only place I could stick it would be right here. So I'd stick in H right there. What about if we're dealing with pH of 9? That's basic. That means I'm going to take an H plus. Where can I take an H plus? I can take it from here. This will change to H2N. We lose the charge as well because the plus goes with the H that's disappeared. And again, this test is, these tests are multiple choice, so you're not going to be actually drawing things like this, but you may have to identify which one would go with which. So I could draw it with, an H here, or I could draw it down in H here and ask which sort of situation it's in. So amino acids like to chain together. In the way that they stick to each other or chain together is known as a peptide bond. So we're moving into proteins. So we're taking those 20 amino acids, which are sort of like the pearls, and we're going to string them together in a certain order. Let's say we have a couple different colored pearls. The way that they're going to get strung together or stuck together is a peptide bond. So the linking of 2 or more amino acids by peptide bonds form what's called a peptide. So if you've ever heard of peptide, that's a couple amino acids together. A peptide bond is an amide bond that forms when the COO group of one amino acid reacts with the NH3 plus of the next amino acid. So I'll show you guys how that sticks together. The linking of 2 or more amino acids by a peptide bond forms a peptide. If we have 2, we call it a dipeptide. If it's 3 amino acids, it's a tripeptide. If it's 4 amino acids, it's a tetrapeptide. At some point, we get into what we just call a polypeptide, which is just a bunch of these peptides stuck together, or amino acids stuck together. Where does the bond come into play? You do need to know what a peptide bond is. So I've got glycine over here. Everything is the same. This is the R group. I'm going to circle out the R group so we can sort of ignore it. Okay, here's the R group here. This is alanine. These are the two simplest amino acids. Here's the R group there. So we're really just looking at what its base is doing. Well, the O, that's single bonded to the carbon, and the H, or one of the H's from the NH3 group, are going to dissociate. They're going to come off. So this thing is going to pop off, and not just this, actually two of the hydrogens, my bad. So these two and this are going to pop off to form water. Okay, if the water comes off, so we lose this thing and we lose this thing and we lose this thing, well then the carbon has an open spot and the nitrogen has an open spot, so they will stick together with a bond right here. This is called the N-terminal end because it's the N side. This is called the C-terminal end over here. And this thing right in here, this is our peptide bond. And if you notice, this is open now to bond with another carbon terminal end of another amino acid. And this C terminal end is open to bond with another N terminal end from another amino acid. So we can start chaining a bunch of these things together to get a polypeptide. So here's our glycine, here's our alanine, and then we've brought them together. We can see that the carbon is now, here was the carbon and here was the nitrogen. There was sort of some things in the way, right? Well, the one oxygen disappeared and two of these hydrogens disappeared to form a water. And then that carbon and that nitrogen can come together directly to form our peptide bond. And then they came together and they formed what's known as a dipeptide, and this is glycylalanine, or we could abbreviate it by saying gly-ella, or GA. Okay, so this here says draw the dipeptide for serine and threonine. If I've got this here and this here, what I'm going to do is take this and this, and these I'm going to try and bond together. So the oxygen and two of these hydrogens need to come together to form water. And then the carbon will bond with the nitrogen. This nitrogen has a hydrogen. And then I'm going to fill it in. So from there, I've got a double bond to my oxygen. This is bonded to that CH. That's bonded to the NH3 plus. That's bonded to the CH2, to the OH. All the rest of that's the same. And then let's continue here. This N group is bonded to that CH there, which is bonded to its C terminal end. And then it's got its accessories. It's CH, OH, CH3. But this here being the peptide bond that we got from right there. There we go, a little neater. So looking for that peptide bond, I can see it right here. It's sort of the seam between the two different amino acids. With the exception of the C terminal, so this one over here, when we're naming these, we take, we add a YL. So this is alanine, this is glycine, and this is serine. We would call it alanyl glycyl serine. The C terminal end, we read it like a book. The C terminal end, the one all the way to the right, we just use the full name. right? Or alglycer. Here is one peptide bond. Here is another peptide bond. So write the 3-letter abbreviation for this tetrapeptide. Just do the 3-letter. You don't have to write the YLs. Oh, and then we're done. I would have just kept talking for like another 20 minutes, I think. I don't know why. But it's 12:15. All right, so for this, you just do the first 3 letters. ALA, LEU, CYS, MET. If you wanted to know the name, alanyl lucylcysteine. That's all I got. Yeah, that's as good as it's going to get from me. Biochem was not my strong suit. Cool. There's the peptide bond, peptide bond, peptide bond. Between 4 of them, you would have 3 peptide bonds. So we'll leave it at that. On Thursday, we'll come back and talk about primary structures and how these make different things. And you're good to go. If you have a question, hang around. Otherwise, enjoy the rest of your day. And I will see you for our last lecture on Wednesday. All right.